Welcome back. In the last video, we set up a loss function and we set up an optimizer and we discussed the roles of each. So the loss function measures how wrong our model is. The optimizer talks to the loss function and goes, well, if I change these parameters a certain way, does that reduce the loss function at all? And if it does, yes, let's keep adjusting them in that direction. If it doesn't, let's adjust them in the opposite direction. And I just want to show you, I added a little bit of text here just to concretely put down what we were discussing. Inside the optimizer, you'll often have to set two parameters, params and LR, where params is the model parameters you'd like to optimize. For an example, in our case, params equals our model 0 parameters, which were, of course, a weight and a bias, and the learning rate, which is LR in optimizer. LR stands for learning rate. And the learning rate is a hyperparameter. Remember, a hyperparameter is a value that we, the data scientist or machine learning engineer, sets, whereas a parameter is what the model sets itself. Defines how big or small the optimizer changes the model parameters. So a small learning rate, so the smaller this value, results in small changes. A large learning rate results in large changes. So another question might be, well, very valid question. Hey, I put this here already. Is which loss function and which optimizer should I use? So this is another tough one because it's problem specific. But with experience in machine learning, I'm showing you one example here. You'll get an idea of what works for your particular problem. For a regression problem like ours, a loss function of L1 loss, which is MAE in PyTorch, and an optimizer like torch.optim/SGD, like stochastic gradient descent, will suffice. But for a classification problem, we're going to see this later on. Not this one specifically, whether a photo is a cat or a dog. That's just an example of a binary classification problem. You might want to use a binary classification loss. But with that being said, we now are moving on to, well, here's our whole goal, is to reduce the MAE of our model. Let's get the workflow. We've done these two steps. Now we want to build a training loop. So let's get back into here. There's going to be a fair few steps going on. We've already covered a few, but hey, nothing we can't handle together. So building a training loop in PyTorch. So I thought about just talking about what's going on in a training loop, but we can talk about the steps after we've coded them. How about we do that? So we want to build a training loop and a testing loop. How about we do that? So a couple of things we need in a training loop. So there's going to be a fair few steps here if you've never written a training loop before, but that is completely fine because you'll find that the first couple of times that you write this, you'll be like, oh my gosh, there's too much going on here. But then when you have practice, you'll go, okay, I see what's going on here. And then eventually you'll write them with your eyes closed. I've got a fun song for you to help you out remembering things. It's called the Unofficial PyTorch Optimization Loop Song. We'll see that later on, or actually I'll probably leave that as an extension. But you'll see that you can also functionize these things, which we will do later in the course so that you can just write them once and then forget about them. But we're going to write it all from scratch to begin with so we know what's happening. So we want to, or actually step 0 is loop through the data. So we want to look at the data multiple times because our model is going to, at first, start with random predictions on the data, make some predictions. We're trying to improve those. We're trying to minimize the loss. To make those predictions, we do a forward pass. So forward pass, why is it called a forward pass? So this involves data moving through our model's forward functions. Now, I say functions because there might be plural, there might be more than one. And the forward method, recall, we wrote in our model up here. Forward. A forward pass is our data going through this function here. And if you want to look at it visually, let's look up a neural network graphic. Images, a forward pass is just data moving from the input to the output layer. So starting here, input layer, moving through the model. So that's a forward pass. Also called forward propagation. Another time where more than one name is used for the same thing. So we'll go back down here. Forward pass. And I'll just write here. Also called forward propagation. Propagation. Wonderful. And then we need to calculate the loss. So forward pass, let me write this. To calculate or to make predictions on data. So calculate the loss, compare forward pass predictions. Oh, there's some thunder going in the background here of my place. We might be in for a storm. Perfect time to write code. Compare forward pass predictions to ground truth labels. We're going to see all this in code in a second. Calculate the loss, and then we're going to go optimize a zero grad. We haven't spoken about what this is, but that's okay. We're going to see that in a second. I'm not going to put too much there. Loss backward. We haven't discussed this one either. There's probably 3 steps that we haven't really discussed. We've discussed the idea behind them, but not too much in depth. Optimizer step. So this one is loss backwards is move backwards. If the forward pass is forwards, like through the network, the forward pass is data goes in to out. The backward pass data goes, or calculations happen backwards. So we'll see what that is in a second. Where were we? Over here. We've got too much going on. I'm getting rid of these. Moves backwards through the network to calculate the gradients. The gradients of each of the parameters of our model with respect to the loss. Oh my gosh, that is an absolute mouthful, but that'll do for now. Optimizer step. This is going to use the optimizer to adjust our model's parameters to try and improve the loss. So, remember how I said in a previous video that I'd love you to watch the 2 videos I linked above, one on gradient descent and one on backpropagation. If you did, you might have seen like there's a fair bit of math going on in there. Well, that's essentially how our model goes from random parameters to better parameters using math. Many people, one of the main things I get asked from machine learning is how do I learn machine learning if I didn't do math? Well, the beautiful thing about PyTorch is that it implements a lot of the math of backpropagation. So this is backpropagation. I'm going to write this down here. This is an algorithm called backpropagation, hence the loss backward. We're going to see this in code in a second, don't you worry. And this is gradient descent. So these 2 algorithms drive the majority of our learning. So backpropagation, calculate the gradients of the parameters of our model with respect to the loss function, and optimizer step will trigger code to run gradient descent, which is to minimize the gradients. Because what is a gradient? Let's look this up. What is a gradient? I know we haven't written the code yet, but we're going to do that. Images. Gradient, there we go. Change in y, change in x. Gradient is from high school math. A gradient is a slope. So if you were on a hill, let's find a picture of a hill. Picture of a hill. There we go. This is a great big hill. So, if you were on the top of this hill and you wanted to get to the bottom, how would you get to the bottom? Well, of course, you just walk down the hill. But if you're a machine learning model, what are you trying to do? Let's imagine your loss is the height of this hill. And you start off with your loss is really high. And you want to take your loss down to 0, which is the bottom, right? Well, if you measure the gradient of the hill, the bottom of the hill is in the opposite direction to where the gradient is steep. Does that make sense? So if the gradient here is an incline, we want our model to move towards the gradient being nothing, which is down here. And you could argue, yeah, the gradient's probably nothing up the top here, but let's just, for argument's sake, say that we want to get to the bottom of the hill. So we're measuring the gradient, and one of the ways an optimization algorithm works is it moves our model parameters so that the gradient equals 0. And then if the gradient of the loss equals 0, well, the loss equals 0 too. So now let's write some code. So we're going to set up a parameter called, or a variable called epochs, and we're going to start with 1. Even though this could be any value, let me define these as we go. So we're going to write code to do all of this. So epochs. An epoch is one loop through the data. ... So epochs, we're going to start with 1. So 1 time through all of the data. We don't have much data. And so for epoch, so let's go this is step 0. 0, loop through the data. By the way, when I say loop through the data, I want you to do all of these steps within the loop. And do ... loop through the data. So for epoch in range epochs. Even though it's only going to be one, we can adjust this later. And because epochs, we've set this ourselves, this is a hyperparameter because we've set it ourselves. And I know you could argue that, hey, our machine learning parameters of model 0, or our model parameters, model 0, aren't actually parameters because we've set them, but in the models that you build in the future, they will likely be set automatically rather than you setting them explicitly like we've done when we created model 0. And oh my gosh, this is taking quite a while to run. That's all right. We don't need it to run fast. We need to write some more code, Daniel. Come on. There's a step here I haven't discussed either. Set the model to training mode. So PyTorch models have a couple of different modes. The default is training mode. So we can set it to training mode by going like this. Train. So what does train mode do in a PyTorch model? My goodness, is there a reason my internet is going this slow? Well, that's all right. I'm just going to discuss this with talking. Again, list. Train mode. Train mode in PyTorch sets, oh, there we go, requires grad equals true. Now I wonder if we do with torch.noGrad, remember noGrad is similar to inference mode, will this adjust? See, I just wanted you to take note of requires grad equals true. Actually, what I might do is we do this in a different cell. Watch this. This is just going to be, rather than me just spit words at you, I reckon we might be able to get it working doing this. Oh, that didn't list the model parameters. Why did that not come out? Model 0.eval. So there's two modes, eval mode and train mode. Model.eval parameters. Hey, we're experimenting together on the fly here, and actually this is what I want you to do, is I want you to experiment with different things. It's not going to say requires grad equals false. With torch.noGrad. Model 0.parameters. I don't know if this will work, but it definitely works behind the scenes. And what I mean by works behind the scenes and not here, it works behind the scenes when calculations are being made, but not if we're trying to explicitly print things out. Well, that's an experiment that I thought was going to work and it didn't work. So train mode in PyTorch sets all parameters that require gradients to require gradients. So do you remember with the picture of the hill, I spoke about how we're trying to minimize the gradient? So the gradient is the steepness of the hill. If the height of the hill is a loss function and we want to take that down to 0, we want to take the gradient down to 0. So same thing with the gradients of our model parameters, which are here, with respect to the loss function, we want to try and minimize that gradient. So that's gradient descent, is take that gradient down to 0. So model.train, and then there's also model 0.eval, so turns off gradient tracking. So we're going to see that later on. But for now, I feel like this video is getting far too long. Let's finish the training loop in the next video. I'll see you there.